Okay, so yeah, click everything closed. This is stuff that you have never seen before. It's completely new, and so you're gonna have to really pay close attention because you're not gonna have any idea about any of this stuff. So what I wanna show you today, we're gonna get kind of through probably, well, I mean, to some degree, we'll get through the first 4. We won't get a lot of practice with step 5. So I wanna show you how to use matrices to solve linear systems, how to represent a linear system with a matrix, and then how to do what are called elementary row operations to get a solution. What this really means is just kind of a shorthand approach to all the stuff you already know how to do, right? But without having to write so much, and it's more efficient, it's quicker. So first of all, how do we make the switch from a linear system with variables to a matrix? So what is a matrix? A matrix is a rectangular array of numbers. That's it. An array just means a pattern, right? Like if you're coding, you deal a lot with matrices and arrays. A lot of times you call them arrays, but really what an array is just could be viewed as a matrix. So for example, if I want to describe a matrix, I have to talk about the size of the matrix first. A matrix is organized by the rows of the matrix, or makes sense. Those would be the horizontal collections of numbers, and the columns, which would be the vertical collections of numbers, right? And we would say that, for example, this matrix is a 2x3 matrix because it has 2 rows and 3 columns. You always list the number of rows first, and the number of columns second, right? So it's a 2x3 matrix. Now the way we develop a matrix is by writing all of the equations in standard form. Notice we don't care if the leading coefficient is positive or negative. We would like if possible, we would like all of the elements of the matrix. The individual numbers in a matrix are called the elements. Those correspond to the coefficients in the equations. We would really prefer to avoid fractional coefficients if we could, but they would still work, technically. They're just more awkward, so we'd prefer not to use those. So we write the system in standard form where the x term comes first plus the y term equals a constant, and then we just take the coefficients and translate those into the rows in the matrix, right? So if we look at this transition, everybody agree that the top row, row 1, corresponds to equation 1. Row 2 corresponds to equation 2. And column 1 in the matrix would just be the coefficients of x. Column 2 would be the coefficients of y. And column 3 would just be the constants on the other side of the equation. Sometimes when you're writing, this is called an augmented matrix, because it includes the stuff on the other side of the equation. Sometimes people put a little dashed line there that represents the equal signs. I don't do that. I mean, you can if you want to, but it just takes more time to do. So what do we do with a matrix? Well, there are 3 elementary row operations that we're going to talk about, and that's it for our class. There are some other things you can do with matrices. You can invert matrices, you can calculate determinants, you can do all kinds of other more complicated things that we don't really need to do, though, to accomplish our goals here. So the row operations, these are the 3 row operations. And what I want you to try to connect here is make the connections between these row operations and the things you would do, the steps you would take to algebraically solve a linear system. Well, one thing we can do is we can interchange the rows in a matrix. That's no big deal, though. Interchanging the rows in a matrix would just mean writing the equations in a different order. That's fine. It doesn't make any difference which equation we write first and which one we write second. Agreed? We can multiply or divide all the numbers in one row by the same number. Well, we do that all the time when we're solving equations, right? Don't we multiply, like when we were using elimination, wouldn't we in this case like multiply the bottom row by -2, for example, right? Or sometimes if we want to solve for a variable, we'll divide both sides by a number. Same thing. Instead of dividing by a number, though, with row operations, it's always easiest to multiply by a fraction instead. Like dividing by 4 would be the same as multiplying by 1/4, exactly, right? Okay, and then the third thing is the elements of any row may be multiplied or divided by a non-zero number and then added to the elements in another row. Okay, that seems like a lot of stuff, but again, you've done this. We've done this before. Where did I want to go with that? No, I'm going the wrong way. Like if we were solving this system using elimination, wouldn't you multiply the bottom equation by -2 and then what? We'd multiply the bottom one by -2 and then what did we do? We added them up, right? We added them to cancel, to eliminate a variable. Agreed? Okay. Well, that's all that this third row operation is. Same thing. Multiply one row by a number and add it to another row. Same step, right? So these are all the same algebra steps you've already done algebraically solving systems. It's just a lot quicker and more efficient to do it with a matrix. Okay? So there's one way we can do this is we want to use row operations to get the matrix into what's called row echelon form or triangular form. Okay, what do you notice about this form? This is where we want to get where we can stop using matrices and just solve the system. What does that bottom row say? It says 0x plus 1y equals c. Isn't that just the same thing as saying y equals c? Ah, okay. Well, if I know, and if a, b, and c are just numbers, then that's telling me y equals a number. What could I do now to solve for x? What does the top row say?
1x plus ay equals.
Okay, well, if I know that y equals the number c, couldn't I just substitute that into the top equation to solve for x? Everybody agree?
Yeah.
So that's just called back substitution. And once we get a matrix into this form, it's really simple for me to just know the value of one variable and back the value of the other variable, right? So what does this mean, this row echelon form? What are the characteristics here that are important? There's a couple of them. What do we notice about the top row that's important, you think? The 1. Yeah, we want to have a 1 for our coefficient of x. Bottom row, there are two things that are important. What are they? Okay, I want a 0 there, and I want a 1 there. Okay, and that's, so really that just means if you look at this descending diagonal, we call it, the descending diagonal would have all 1s. And as we move down the matrix, we're just going to contribute zeros in front of the 1s as we move down the matrix. Okay? And then once we get to that form, we're done with row operations and we just solve the equation. Okay, let's try this. Let's try this with something like this guy. Here's our, everybody give me 1 to 5 on this. Does everybody see how we got from the linear system into a matrix form? Okay, we good with that? Okay, now let's do some row operations. Remember, my goal is to get this thing to look like 1, 0, 1, right? Okay. Well, there's one pretty easy thing I could do to get a 1 on top. What's that? What could I do? I could, you're right. I could even do something easier. I mean, I already have a 1 as my leading coefficient in the bottom row, so just interchange the rows. Just flip them. If I put this one on top, then we're good, right? That one's already got a 1 there. Everybody see that? So step 1, how do we say that? Here's how we say it. We're going to interchange rows and 1. Rows 1 and 2. R1 and R2 get exchanged. And we get that. Okay? Okay, so top row, done. Now we got to work on the bottom row. What could I do on the bottom row? My goal is to get a, what needs to be there? 0. Okay. How could I get a 0 there? What could I do to get a 0 there? subtract 2 from the, okay, I see what you're saying. Okay, but we have to, it has to be a combination of something we do with the, all I could do is multiply that row by something. Does that make sense? I could multiply, but if I multiplying by 0 doesn't do anything, because then I just get zeros everywhere. How could I combine it with the top row? What would you guys do if we were using elimination? And I wanted to, what would you multiply the top one by? -2 and then add them together? Something like that? Okay, so let's do that. Let's do that. Let's multiply top row by -2 and add it to the bottom row. And that's what we're going to use to replace our current bottom row. So how do we read this then? What this is telling me is row 2 is being replaced by that row operation. We're going to replace row 2 with -2 R1 plus R2. Okay, so what's that give us? Top row stays the same. What's that give us for our first element? What's -2 times 1 plus 2? 0. Okay. What's -2 times 3 plus -1? -7. What's -2 times 11 plus 8? -14. Good? What was good about that, what we just did?
Got the 0.
Oh, good. Okay, we got the 0. Right? Whoops. That was good. Okay, now what's the next thing we need to change? Say it again. The -7 needs to be a 1. Okay, that's easy to do though, right? We need to make this into a 1. What's the only thing I have to do to row 2 to make that a 1? Divide by -7, which is the same as multiplying by -1/7, right? Okay, give me thumbs on that. Everybody see that? Okay, so our next row operation, oops, is going to be that. Row 2 is going to be replaced by -1/7 times row 2. Okay, everybody good? Okay. So that gives us what? -1/7 times 0 is 0. Okay, so that multiplying by some number, 0 times a number, what's cool about that is it leaves it a 0, right? So we still have what we need there is a 0. -1/7 times -7 is 1. -1/7 times -14 is 2. Okay, we're done. We got that thing into triangular form or echelon form. So what does the bottom row tell us? Y equals 2. What does the top row tell us? Okay, solve that system. That's pretty easy, right? We know y equals 2. If I substitute that into the top, don't we just get x plus 3 times 2 equals 11? Solve that in your head. What do you get? X equals 5, yeah. Subtract 6 from both sides, and we got it. So we got our solution, okay? So that process that we just did of putting a matrix into echelon form is called Gaussian elimination, just using those row operations to get the matrix into that form. I mean, you could look back at this and you could see each one of those maneuvers that we did, each one of those row operations really just corresponds to some algebra that you would have done if you were solving the system using algebra. Do you see the advantage of this though, how easy it is? You don't have to write down variables, right? You're able to just really quickly and compactly do these row operations and manipulate that system and get to a solution, right? It's not, you may be thinking, well, that's not that big a deal. I mean, I could have solved that pretty easily using algebra, and that's true. But when you expand this to bigger linear systems, the difference becomes really appreciable. Like if you're solving big linear systems using row operations, like how much fun did you have, be honest, solving those 3x3 linear systems with algebra? It's a lot of writing, isn't it? It's, you got to write down a lot of equations. There's a lot. This is going to be so much easier to do. You're going to like this. Yeah, yeah, and we'll do that today. We'll just expand this to do, deal with bigger systems. Okay, so let's try this guy. So everybody agree that's my system? Okay. All right, so what are some things I could do here? Like the top row, I don't think I did this when I wrote out this solution. The top row, technically, I probably should multiply through by what? -1 to make that a 1, right? And we could do that at some point. I just jumped right into trying to make that a 0 on the bottom. As it's currently written, how would that look? What would be the row operations to make this a 0? Think about that. What's that going to be? I could multiply by 1/3. That'd be a pretty easy way to do it. Okay. What's another way? That would be fine. I could just do replace R2 with 1/3 R2. Would be a great way to do it. What's another way? How could I combine it with row 1?
3 times row 1.
Yeah, 3 times R1 plus R2. Everybody see? Okay. That's what I did. Probably better just to multiply by 1/3 though. Okay. Oh, but hold on. I'm trying to get, never mind. Because what are we trying to get there?
0.
0. Yeah.
So 1/3.
So 1/3 would make that a 1, and then I could just add them together, I guess, right? But we'll just do this. We'll do bottom row gets replaced by 3R1 plus R2. Okay? So what's that going to give us for that spot? 0. 3, because how come? 3 times -1 plus 3 is 0. 3 times 3 plus -9 is 0. 3 times 6 plus 9 is 27. Okay, what in the world does that mean? Yeah, no solution, right? How come? Because look what that bottom row is telling us. It's telling us that 0 equals 27, which is false. So we know what that is. That's no solution, right? And for a two-dimensional system, that means the lines are what? Parallel. Yeah, we just have parallel lines, don't we, right? That makes sense? Because we're dealing with, what was our linear system? We only had 2 variables, so each of those linear equations just represents a line in the xy plane, right? Okay? All right. Everybody agree that's my matrix?
Yes.
Okay. So I want to get a 1 in the top, but I just jumped right into trying to get a 0 as my first element in the bottom row. Okay, and I can do these in any order. I don't have to get a 1. I don't have to make that a 1 first. And sometimes, as you'll see here, sometimes it's easier just to make that a 0 before I try to make that a 1. What would my row operations be to get a 0 here? 2R1 plus R2. And that's how I'm going to transform row 2. So, everybody buy that? Row 2 gets replaced by 2R1 plus R2. Okay. So what is 2 times 9 plus -18? 0, right? Okay, that's the whole point. What's 2 times -3 plus 6? 0. What's 2 times 6 plus -12? 0. Okay, so what's that mean? Same line. Yeah, because now I get the true statement, 0 equals 0. Okay, good? So this works for all the situations we dealt with before. These row operations get us there too, right? And always the bottom row is what reveals if this is no solutions or infinite solutions, right? Okay? So we'd say that's a consistent dependent system, right? We talked about that stuff. Okay, so now plan B. Plan B is don't stop at echelon form, right? We stopped here and had to use back substitution to solve for the other variables. We solved for one variable and had to use back substitution to find the other ones, right? With a 2x2 system, that only means one substitution, but if this were a 3x3 system, I would get a solution for z, and I would plug that into row 2 to get a solution for y, and I'd plug both of those into row 1 to get a solution for x, right? There's a lot of back substitution there. Not that it's so hard to do, but plan B would be keep going, and instead of leaving this in row echelon form, we could put this in reduced row echelon form, which looks like this. Just keep going with row operations instead of transitioning to regular algebra until we get the matrix to look like this, where the descending diagonal would be 1s, just like before, but all the other elements on the left side of the equation are 0s, right? Or if it's 3x3, it would look like that. We get descending diagonal with 1s, and all of those are 0s, and those are 0s. Okay, we don't have to do anything then. That solves the entire system, right? So what does this tell us in this 2x2 system? What's that first row tell us? Yeah, x equals a. What's the second row tell us? Y equals b. If we're solving a 3x3 system, what's the first row tell us? What's the second row tell us? What's the third row tell us? Okay, so my preference is always to keep going and use row operations to put this thing into reduced row echelon form, because row operations are more efficient than writing down algebra. Okay? So let's do one of these. Let's take this one, and let's do it both ways. First of all, let's put this into just triangular form, row echelon form, and then we could use back substitution, and then we'll see how we could have kept going to put this into reduced row echelon form to get right to the solution. Okay? Everybody agree, first of all, with our matrix? Give me 1 to 5 on that. Everybody see how we set that up? Okay? All right, so what's good?
The top row.
Yeah, look at that. Top row, we got a 1 where we want it, right? So that's good. This is good. Some of our work is done for us. Okay, what do we need the rest of this matrix to look like? So what does row 2 need to look like? 0, 1, something, right?
Yeah.
Row 3 has to look like 0, 0, 1, something. Okay? So how are we going to get there? So we got to work a little bit at a time. So our first step is going to be we want to turn both of those into zeros. Okay? Anybody see that? That's our goal. We want to get zeros there, and once we get zeros there, we'll try to get a 0 there. Okay? Right? Give me 1 to 5. You see how that kind of, we're just going to have to whittle away at this. These are, honestly, I mean, you got to kind of embrace your inner nerd a little bit with this stuff, and just, this stuff is kind of fun. I mean, it's like doing a puzzle. Every time you solve a matrix, it's just like doing a puzzle, and you're just going to put together the row operations until you solve the puzzle. So what are some things, how could we, for example, get a 0 there? Okay, so I could do 3R3 plus R2. Everybody agree? Okay, good. So top row will stay the same, 1, 1, 1, 9. Bottom row will stay the same, -1, 2, -3, -2. But the middle row is going to be replaced by, you told me, 3R3. Plus R2. Okay, give me thumbs on that. Does that make sense? Okay, so what's that going to become then? 3R3 plus R2. So 3 times -1 plus 3 is 0. 3 times 2 plus -1 is 5. 3 times -3 plus 1 is -8. 3 times -2 plus -1. He said 3R3, so 3 times -2 plus -1. Negative 7. Good. Okay, that's good. We got a 0 where we wanted it. Okay, we said we also need a 0 there though, right?
Yeah.
Okay, what's a pretty simple row operation to get a 0 there?
R1 plus R2.
Yeah, R1 plus R2. Everybody see that? Okay. So down here we'll just do R1 plus R3. Okay. Top two rows stay the same. 1, 1, 1, 9, 0, 5, negative 8, negative 7. Bottom row becomes 0. That plus that is 3. That plus that is, that plus that is 7. Okay, good. What's next?
Negative 3 R1 plus R3. So we need to get that.
Okay, yeah,
0, right?
yeah, that's good. Negative 3, well, okay, there's a problem with that.
Why?
You said, what am I trying to accomplish here?
Get that 0 eliminated. I mean, that 3 eliminated.
I want to get the 3 eliminated, right?
Yeah, yeah,
Good.
yeah.
Okay, you said negative 3 R1
Yeah, because then you add the
plus this one, but what's that going to give us there? Yeah, it's not, we're going to keep that as 0, right? So look what our goals are. We got to keep that as 0, but make that
a 0.
okay. So now, what are the ways to do that? There are a couple ways to accomplish this. But the easiest way, we have to really, we don't want to use row 1 because row 1 has a 1 there, which is a problem for us, right? I need to somehow just use rows 2 and 3. So how could I somehow get a 0 there using rows 2 and 3?
Negative 3 times row 2 plus plus 5 times row 3.
Yeah. Everybody see that? Okay. Right? And we could break that into separate steps, but we could also just kind of power through it and do that as one big step.
Okay, okay.
Does that make sense?
Yeah, gears are turning now.
Okay. Okay. So let's do, whoops. So row 3, we're going to make that, what did we say we were going to do? We're going to do 3 row 2. Say it again.
Would it be negative 3 row 2 and then plus 5?
That's fine. You could either do negative 3 row 2 plus row 3, or you could do 3 row 2 minus 5 row 3. See what I'm saying? I think I said that wrong, but you get the idea? We just have to get, what would you be doing if you were using elimination? You'd be multiplying this row either by negative 3 and this one by 5, or you'd be multiplying this row by 3 and this row by negative 5, right? To get those to cancel. Because I want to get negative 15 for both of those, I want to get 15 and negative 15 and then add them up. Is that making sense? Okay. So we could do bottom row then. I'm going to do it this way. I'm going to say 3 R2 minus 5 R3. Technically, we're supposed to break that up into 2 separate row operations, but I always cheat. I mean, I don't want to write it out twice. We'll just do it as one big row operation. Okay, the rest of it stays the same. So this is 1, 1, 1, 9, 0, 5, negative 8, negative 7. And then what in the heck's that bottom one going to become? So this is going to be a load. We got to think about this. So 3 R2 minus 5 R3. So 3 times 5 minus 5 times 3 is 0. So we already had a 0 there. That gives us a 0. 3 times negative 8 is what? Negative 24 minus 5 times negative 2. So plus 10. So what is that?
Negative 14.
Negative 14,
Yeah.
right? Okay. Okay, and this is a big one. 3 times negative 7, so that's negative 21, right? Minus 5 times 7. Okay, so minus 35. So we got, what is that, 56? Okay, so negative 56, agreed? Okay, it might have been easier to do this in separate row operations. But you could, right? We could have just started off by multiplying, we could have multiplied the middle row by 3 and left it. You see what I'm saying? We could have split those up into separate row operations if we really wanted to. Okay. All right. Hey, we're almost there. Look at this. We're pretty darn close, right? Pretty darn close. What's all we have left to do?
The diagonal.
Need to make the diagonals into 1s. Well, one of those is really easy to do. Bottom row is really simple. How do I make that a 1? Multiply both sides by? I'm dividing both sides by what? By negative 14, right, to make that a 1, which is the same as multiplying by negative 1/14. Okay, so then we could just do this, right? We could make the bottom row is just going to be negative 1/14 times R3. R3 is replaced by negative 1/14 times R3, which is just going to be 0. Negative 1/14 times 0 is 0 times 0 is 0. Negative 1/14 times negative 14 is 1. Negative 1/14 times negative 56, well, that's the same thing as 56 over 14, which is 4. Hey, there's one solution. What's Z?
4.
4, okay. Rest of it stayed the same. Okay. Last step, we'd like to get this to be a 1. So what could I do? What could I do? I could multiply by 1/5.
Okay.
Yeah, I could. That's fine. I could multiply by 1/5. What's the only disadvantage of that?
Fraction.
I'm going to get a fraction. Yeah, I'm going to get a fraction. Is there another way? How could I combine it with the bottom row? Actually, hold on. There really isn't a way, is there? No, we're stuck. We'd have to multiply by 1/5, right? We'd have to multiply by 1/5, yeah. It's a bummer, isn't it? Yeah. Okay, so then we get, there's no other way about it. To make that a 1, we're just going to multiply by 1/5. Yeah. Okay, there is another way we could sidestep that, but I think it's pretty tricky. I don't want to do it. So we're just going to multiply by 1/5. So the middle row is going to become 1/5 R2. And what does this become then? We get 1, 1, 1, 9. Bottom is 0, 0, 1, 4. What's the middle row become?
0, 1, negative 6.
And say it again.
Negative 17.
So we're there. We're into echelon form. Now let's just convert this back to a linear system and solve it. Okay? So what does the top equation become?
1x plus y plus z equals 9.
What's the middle row become?
Y minus 8 fifths z equals negative 7 fifths.
Okay, bottom row.
Z equals 4.
So we're part way there. So what would we do to solve?
Plug it in.
We just work our way up from the bottom, right? So we'd substitute into the middle equation, and that's going to give us y minus 8/5 times 4 over 1 equals negative 7 over 5. So what's that give us then? We're going to get So y minus 32 fifths equals negative 7 fifths. Last step. Add 32 fifths to both sides. And that gives us y equals 32 fifths minus 7 fifths, which is how many fifths? 32 minus 7? 25 fifths. What's 25 fifths? Ah. Okay. And then next step, we know z and y. Now what?
X is 0.
Yeah, plug them in into the top row, right? So this is going to become y is 5, z is 4. Pretty trivial to solve for x. What do we get? 0, right? X plus 9 equals 9. So x equals 0. Agreed? Okay, let's go back to here. And I want to show you how you could do that. Well, you guys, I don't have to show you. You show me how we could have maybe done this a little bit better. Okay. Okay, would there have been a way to, okay, we actually kind of missed a step here. Would there have been a way for us to easily get a 1 there? So we could have avoided having all these fractions. Because think about this. Why did we have to deal with all the fractions? Yeah, because we had to divide by 5, because that had already become a 0 and a 0, right? See what I'm saying? Could we have, before we did that, could we have found a way to turn that, get a 1 in the middle row for our leading coefficient? That would have been kind of handy, wouldn't it?
We could just swap the negatives that we did for negative.
How could I here have combined rows 2 and 3 to get a 1 there?
Multiply the bottom row by 2 and the middle row by -1.
Yeah, okay. Everybody agree with that? I could have done 2r3 minus r2. Everybody with me? Okay. So this is kind of fun. I mean, we're just doing a puzzle, right? And one of the goals is to avoid fractions, because fractions are just kind of a pain, right? So what did we learn from that? Well, I'm going to go back to here. Go back to that step. Right? We could have maybe taken a better path by getting that to be a 1. Okay? And you guys already figured it out. We'd leave the top one alone. So moving forward, how does that impact our strategy? Well, our strategy is, before we get this to be a 0, we want to finish this middle row and make that a 1. Okay? So our next step would have been, you guys told me correctly, it was going to be row 2 gets replaced by 2r3 minus r2, right? Okay? Well, what goes there, obviously? 0. 2 times 0 minus 0 is 0. That's the nice thing. Row operations on 0 always give you 0, right? Okay, so 2 times 3 minus 5 is, okay, 2 times negative 2 minus negative 8 is, so that gives us negative 4 plus 8, right? Right? 2 times negative 2 is negative 4, minus negative 8 is plus 8. Negative 4 plus 8 is,
Negative 4.
no,
What?
positive
Oh,
4.
yeah, you're right.
Okay, 2 times 7 is 14, minus negative 7 is plus another 7. Ah, okay. That's better, isn't it? And now that that's a 1, it even makes it easier to get rid of that 3. What would I do to get rid of that 3? What would my next row operation be? Even just to put this into regular echelon form, we could have done this without fractions. What am I going to do to make that a 0? 3R2 minus R3, right? Everybody see that? Okay, good. So middle or bottom row becomes 3R2 minus R3. Top rows stay the same. Okay, so what is the bottom row going to be then? 3 times R2, 3 times 0 minus 0 is 0, right? Okay, good. Whoops, I want that to be purple. 3 times 1 minus 3 is 0. 3 times 4 is 12, minus negative 2 is 14. 3 times 21 is 63, minus 7 is 56. Right, what would my next row operation be? Multiply by 1/14 in the bottom row. And doesn't that just give me, I'm going to do this fast, doesn't that just give me, it gives me 0, 0, 1, 4?
Yeah.
Okay, good. All right, we'll get back to this tomorrow.